I want to say just a little bit more about the neutron star and the stellar black hole, or the black hole that's formed as a massive star ends its life. So the thing about the neutron star is that actually during when that star was alive before it blew up, for massive stars, 8 solar masses and higher, they get more, their core gets more and more dense. So honestly, then we have the explosion process, which doesn't help, or it kind of increases potentially the density situation. So we end up with a very dense object, whether it's a black hole or a neutron star. So specifically, if we were to take a tablespoon worth of a neutron star and come back on Earth and weigh it, it would weigh 1,200 tons. So it's very dense. We talked a little bit in chemistry about the structure of an atom, and the density is so that basically the atomic structure of the matter that makes up that neutron star has been so affected that, how does this work? Protons and electrons, okay, so protons are in the nucleus, electrons are outside the nucleus, have combined to actually form more neutrons. Sometimes I think of a neutron star as kind of neutron soup, so that's kind of fun. So one of the things about these celestial objects, like a neutron star or a black hole, you're like, really, Mrs. Stipes, how do we know that they're there? And neutron stars, the way they're set up, if they're kind of the direction is in favor of it, they can send Earth a signal, and the signal they send is called a pulsar. And I'll try to kind of describe what that looks like. So here we have our neutron soup object, and here we have it spinning on its axis of rotation, just kind of like the Earth spins on its axis of rotation. Now, one of the things about how fast it's spinning is kind of crazy. It's like, it's called the conservation of angular momentum. It's like if a skater has her arms spread out, when she brings her arms in, she goes faster and faster and faster. So that's the conservation of angular momentum. So basically, as the star used to be pretty big, it had some sort of spin to it, and as its material came closer and closer to its center, it spun faster and faster. So we have a very fast spinning object, and that fast spinning object, related to the charged particles that some it still has left, creates this magnetic field. So here we have a magnetic field kind of squirting out, not necessarily along its line of spinning, along its rotational axis. And so in doing so, basically, we have kind of a coning sort of, it's called like a lighthouse sort of thing. So we have basically a coning signal of electromagnetic radiation kind of spinning and emitting here. So if the Earth is in the direction of that signal, we basically get a pulse of energy as it spins. That's a pulsar, and we definitely can see our pulsars going on. In fact, I'm kind of thinking that M1 that I showed you a minute ago with the Crab Nebula, it actually has a pulsar, the signal from a neutron star in the center of it. So that's a neutron star. The other thing is a black hole, right? So we don't only just get black holes when massive stars end their lives. We can also get black holes like they think at the time of the Big Bang. Those are called primordial black holes. And we can also we know that there are supermassive black holes in the center of galaxies. And actually, the Milky Way galaxy has a supermassive black hole in its center, and we're thinking that most galaxies are home to a really big black hole. There are other ways to get black holes, but those are kind of a couple of the top ones that I think of anyway. So we said the neutron star, the matter was so dense that electrons and protons merged to form neutrons. Well, think of it this way then. The matter that makes up a black hole is even more dense than that. It's so dense that basically, as I understand it, kind of the particles have lost their particle identity that makes up atoms. It's no longer regular atom matter. Black holes are made up of material that are just even more of a crazy soup than neutron stars. It's so dense that actually it makes what we call, or what I think of as a hole in the fabric of space and time. I think that is so cool. So here we have kind of your typical stellar black hole, which here, of course, in the center is the black hole, okay, and that's what we call the singularity. We have something called the event horizon, and that is the region beyond which, if you go inside the event horizon, you no longer can escape, because there's this thing called escape velocity. And escape velocity is how fast do you need to be going as a minimum to escape the gravitational pull of the object you're leaving. And the escape velocity, if you are inside the event horizon, is actually greater than the speed of light. And nothing can go greater than the speed of light. So you are just there for the duration. Not are you necessarily just there, but you probably will ultimately fall into the singularity itself. So they call black holes because not even light can escape the event horizon of a black hole. So there again, you might be going, all right, Mrs. Snipes, this is all well and good, but do we know that there are stellar black holes up there? And the answer is yes. Sometimes, if the conditions are right, and actually this is a star right here, this is a live star, and I don't know if you remember, but I said a lot of times stars have companions. So over here we actually have, I'll go ahead and put BH. This is our black hole over here. So it used to be alive, and it ran its life and ended up as the little nugget. The core material was dense enough to make a stellar black hole. So what can happen, and what does happen, we know, is that material from a companion star actually can be drawn, siphoned off by the gravitational influence of the black hole, and it's kind of like a bathtub drain. Okay, it actually will form what's called an accretion disk, and it will pick up speed as it's kind of going down here, getting ready to fall into the black hole itself. But as it's in this accretion disk, it actually heats up, and it emits this, this is saying X-rays, to actually we can see the black hole. Now, do we see the black hole? No, but we see material that is in line to go down past the event horizon into the singularity itself. I think that's it.